There's a recurring fantasy in AI engineering. Teach your model new facts without breaking the old ones, without retraining the whole network, and without playing retrieval roulette on every single query. A new paper from researchers at the National University of Singapore, MIT, and ** calls their answer MEMO, and the architectural bet it makes is more interesting than the acronym. The problem MEMO goes after is one every team running large language models in production has run into, and almost none have solved cleanly. You have a foundation model that knows a lot of general world knowledge. You have a corpus that model doesn't know. Your company's internal documents, a fresh batch of research papers, this week's news, last quarter's earnings calls. You need the model to actually use that new knowledge reliably, updatably, and without making it worse at everything else it used to do well. The existing options are all compromises with sharp edges. Fine-tune the base model on your new data, and you risk catastrophic forgetting, where the model gets measurably dumber at general tasks while learning your specific domain. Use parameter-efficient methods like LoRA or adapter layers. Cheaper, but they still entangle new knowledge with a model's reasoning weights, and they can degrade in unpredictable ways when stacked. Or build a retrieval-augmented generation pipeline. RAG keeps the model frozen, but it turns every query into a search problem with all the failure modes that implies. Irrelevant retrievals. Context window pressure. Latency overhead. Brittle dependence on chunking strategy. Prompt injection through the retrieval channel. MEMO proposes the fourth approach. The researchers train a separate, dedicated memory model that encodes the corpus of new knowledge. They pair that memory model with a frozen base LLM, which handles reasoning and language generation. The base model's parameters are never modified. Only the memory model gets trained, and only on the new knowledge. That separation is the whole architectural point. Corpus knowledge lives in the memory model. Reasoning and language live in the LLM. The two communicate at inference time. When you need to update what the system knows, you retrain the memory model alone, which is smaller and cheaper than retraining a frontier-scale base model, and the LLM stays completely untouched. If this works as advertised, it shifts the operational math for anyone deploying LLMs over proprietary or fast-moving data. You update knowledge by retraining a smaller, isolated component. You don't risk regressing the base model's general capabilities because you never modify them. You can swap memory modules for different domains while keeping a single frozen reasoner. One Llama, one Mistral, one whatever your base is, running underneath everything. And critically, this is not just RAG with extra steps, which is the first reaction a lot of practitioners are going to have. RAG retrieves text chunks and pastes them into the prompt. Retrieval quality caps your performance. Context window caps your scale. The model has to reparse the retrieved text every single query. A trained memory model can theoretically encode knowledge in a more compact, queryable form, closer to how the LLM stores facts in its own weights, but isolated from those weights. That's a different abstraction, not a different RAG implementation. Now, the caveats, because the public summary I have is genuinely thin. The paper has not been independently reproduced as far as I can tell. The benchmarks the authors used, the size of the corpora they tested on, the latency overhead at inference time, the quality of memory model outputs against a strong, fine-tuned baseline. None of that is something I can confirm from a single write-up. I want to see the actual paper, the code, and ideally a third-party reimplementation before calling any of this proven. What I can say is that this general direction has been tried before in many flavors. Memory networks going back to 2014. MEM GPT. Realm. Retro from DeepMind. Retrieval-augmented language models with learned retrievers. React-style agents that maintain external state. The graveyard of clever memory architectures is large, and most of them ran into the same wall. They worked on toy benchmarks and degraded gracelessly at production scale. What would make MEMO actually significant is empirical evidence on three axes. 1. Does updating the memory model preserve the base LLM's general benchmarks? MMLU, human eval, the standard battery, relative to a fine-tuned equivalent on the same corpus. 2. Does it outperform a strong RAG baseline on knowledge-intensive tasks at comparable compute cost, not just against a weak strawman retriever? 3. Does it scale to corpora that RAG handles trivially? Millions of documents, not the carefully curated 1,000-document datasets that always show up in academic papers. The research provenance is worth flagging. NUS, MIT, and A** is a serious collaboration. A** in particular has been doing real systems-level machine learning work for years, and MIT is, well, MIT. This isn't an anonymous preprint from a lab nobody's heard of. That doesn't make the results correct, but it raises the prior that the work was done carefully and the baselines weren't deliberately weakened. If MEMO or something close to it pans out, the winners are obvious. Enterprises sitting on terabytes of internal documents who don't want to ship anything to OpenAI's fine-tuning API or trust a third party with sensitive data. Regulated industries, finance, healthcare, defense, where modifying a base model triggers compliance review and revalidation. Edge deployments where you want one frozen base model with many swappable, domain-specific memory modules running on the same hardware. The losers are less obvious but more interesting. Pure-play RAG vendors should pay attention because their entire pitch is don't fine-tune, retrieve instead. If a trained memory model offers a cleaner abstraction with better recall and lower per-query overhead, the retrieval-as-a-service category gets squeezed from above. Fine-tuning platforms have exposure too, though less because fine-tuning still wins when you actually need to change model behavior, tone, instruction following, output format, not just inject new factual knowledge. What I'd watch for over the next few months. First, a code release. A paper without a reproducible implementation is half a paper, and modular memory systems are exactly the kind of work where implementation details determine whether the headline numbers hold up. Second, third-party benchmarks against strong RAG pipelines. Call BERT-based retrieval hybrid search systems, not the weak baselines that tend to show up in ablation tables. Third, whether the major labs, Anthropic, Google DeepMind, Meta, OpenAI, pick up the approach publicly or quietly ship their own variants in production. When ideas like this work, they tend to surface as features and flagship products before they get formally credited. My honest read. The architecture is intuitive, the problem framing is correct, and the pain point is real. Whether MEMO specifically is the answer or just a useful waypoint toward whatever architecture eventually wins is something we don't have enough data to decide yet. The summary describes the idea. The evidence is what would change the conversation. The broader trend matters more than this specific paper. The industry is slowly accepting that one giant monolithic model trained on everything is not the endgame. Modularity, frozen reasoners, swappable knowledge, specialized memory components, hot pluggable skill modules is the direction the field is moving. MEMO is one more data point pushing that way. The interesting question for the rest of 2026 isn't whether modular memory becomes a standard pattern. It's whose architecture wins, and whether the winning approach comes from academia or from one of the frontier labs quietly building something similar behind closed doors.